give loser bounds for the problems that we care about. We'll see sort of more recent refined GJ-based frameworks which tell you, oh, if the algorithm does these kind of computations, then I can give this bound in the pseudo dimension. Right, so this is what it looks like. So your algorithm takes n parameters, or you can think of n hyperparameters, and it performs two types of operations. So it either does an arithmetic operation, it can take two values, multiply, add, divide, or subtract them, or it could do this conditional statement, could do an if then else, which is basically saying, if you did some computation, it evaluates to something, then do this, otherwise do that. So you have these two kind of computations that you can do, and at the end of the algorithm tells you, it solves some problem. It gives some cluster, some matrix, some regression fit. So this is one of the just ways to express your algorithm. In the end, you will once the algorithm's output is obtained, like a cluster, you will use some utility function to measure its performance, like how close your cluster is to the correct cluster, or how what is the loss of your regression fit compared to the true values, and so on. So there will be some loss to evaluate that output, but this takes into account what operations the algorithm naturally performs on its inputs. We'll see some simple examples of how to apply this, because we feel that this is one of the easier and more accessible tools to give provable guarantees. One of the things to note here is that all the expressions that this GJ algorithm computes are ratios of polynomials in the inputs. So if you are only allowed to do addition, subtraction, multiplication, division, the expressions that you compute will be so-called rational functions or ratios of polynomials in the original parameters. Right, so and we will try to give complexity bounds based on how complex these expressions can get when you're trying to run the algorithm. So that's the high-level idea. So suppose you have n real parameters, and you're trying to determine, you're trying to give a GJ algorithm which tells you whether the algorithm's performance is at least some threshold, so it's like doing at least as well as some benchmark on a given input x. So you fix an input x, you try to run your algorithm on it, and then your algorithm will eventually have some output like a cluster, then you evaluate its performance and you check whether it's good enough. So suppose there's an algorithm which does that, and this algorithm evaluates a bunch of expressions, bunch of conditions, and we say that we give a bound on the number of different expressions it evaluates during the course of its run, and also the complexity of each expression. So all of these are rational expressions, so if we can bound the degree of the quantities that appear in the numerator and denominator, those are the only things that sort of matter in these evaluations. And yeah, don't worry if you think this is too complex, we'll see nice examples of this soon. But just giving these bounds immediately give you a pseudo dimension bound using this theorem, which is basically depends on the number of parameters that are in a hyperparameter family, and also the number of distinct predicates and degrees of the polynomials. Yeah. So just to visualize this a little bit more, so what your algorithm is doing is computing these rational expressions, right? These are ratios of polynomials in the hyperparameters alpha, and then doing a bunch of these computations. In the end, it tells you whether the performance was greater or less than some threshold. So across this tree of computations that your algorithm does, there's a bound on the number of distinct expressions it can use, and in each of the expressions you can bound the degree. And those are the two things you want to try to do in order to understand how complex your algorithm can get. So a simple example of this is linear regression. So you might have seen L2 penalty in linear regression. This is one of the parameters which is very fundamental. It goes by the name ridge regression. just trying to do ordinary least squares regression, but with the L2 penalty term to avoid overfitting and other things. So how do you set the value of the L2 penalty, which is a coefficient of this squared norm, right? So the idea is you have a training set and a validation set, and you want to set your L2 penalty to minimize the validation loss. And if you've seen ridge regression, you might also know that in this case there's a closed form solution given by this matrix inversion. So the only thing you sort of need to do now is to show that this expression can be expressed, to apply this GJ framework, you want to express this expression as a rational function of the hyperparameter. So you want to see, remember the whole big picture is that we want to understand how the algorithm's behavior changes as you change the hyperparameter. So this is one way to quantify that behavior, is to express that behavior as a rational function of your hyperparameter, and that will allow you to give bounds on how complex your algorithm can possibly be. So in this case, you can show one simple lemma which says that it's going to be a rational function with degree at most d, where d is the number of features in your linear regression. You can use this lemma to show that the validation function, which involves squaring, will have a degree at most 2d, and then you can use that to create a GJ algorithm which has degree 2d, and it just evaluates. In this case, it's a simple single predicate that it's going to evaluate whether the validation loss is above or below some threshold. So in this case, it's the theorem directly applies. You can get a pseudo-dimension bound or a sample complexity bound. I will also want to mention, if you're not familiar with learning theory, the significance of these sample complexity bounds are actually twofold. So they not only tell you that this is the amount of data you need to get a hyperparameter which is within epsilon of the best hyperparameter. That's one of the guarantees that you get here. But another guarantee that you get here is what is called as uniform convergence. So what that means, if you bound this with dimension, you get uniform convergence guarantees, which means that if you perform well on the training set, you will generalize well on your test set. So that's which means, like, even if you approximately optimize on your training set, you will be within epsilon of your performance on the training set. So these are really nice guarantees that you can sort of quickly get by applying these tools. Another more complicated example, I will just mention the example. I wouldn't go into the calculations for it, but this is a low rank approximation. So you're given a sparse matrix with the bounded Frobenius norm, and you have a target rank. You want to find a matrix which approximates the original matrix but has a low small rank. So there's an algorithm called the IV algorithm which computes this efficiently, but the algorithm has a parameter in the form of a sketching matrix. Again, I won't go into the parameters and the details. It's a fundamental problem. You have large data sets, you want to approximate them by smaller, low rank data sets so they can preserve their interesting properties and structure, but work with them more efficiently, and you can give guarantees about computing smaller, more efficient approximations of large matrices in this way. So that's widely used algorithm, but another quick example where by analyzing how your algorithm does, you can look at what rational functions it computes and give a bound on the number of rational expressions and their degrees to give a bound on the pseudo dimension. So I think I will give a quick overview of a generalization of this framework. So right now we only work with rational functions, right? So but in practice you see exponential, logarithms, all sorts of other functions. So a very recent work, we extend these rational functions to a much broader class of functions, and gives you this definition of Pfaffian function to motivate this think that will be the last thing we'll look at, last thing standing between the break. So let's look at this function class, because I think that this is a very exciting, much broader function class for which we previously, didn't have tools to bounce with a dimension, but now we can. So what is a Pfaffian function chain? So it's you have a sequence of multivariate functions, right? And you can compute their partial derivatives in terms. You can express their partial derivatives as polynomial of their variables or previous functions in the chain. We'll see simple examples of this soon. But the Pfaffian function chain is basically just a sequence of functions. Each function can be expressed. The derivatives, partial derivatives of each function can be expressed as a polynomial of that function or any of the previous functions in the chain. Once you have this chain, you can construct another polynomial q on top of it, and we call that a Pfaffian function. So there's a Pfaffian function chain. There's a notion of a Pfaffian function, and we will be able to bound. We will be able to allow computations involving Pfaffian functions. So that's the motivation for why we want to study these functions. It's possible to give, analyze the structure of algorithms which involve these computations. So there's this chain length, which is the number of functions in the chain. There's a degree of the Pfaffian degree, which is basically degree of the derivatives, and there's a degree of the Pfaffian function itself, which is the degree of the polynomial q. Let me give you some simple examples. This is all very abstract and very general, but it's actually super simple. So let's look at some examples. So for example, you have this exponential function. So can you try to find the chain length and Pfaffian degree? And this is one of the easier examples. There's a few others. So let's see what would be the chain length, Pfaffian degree, and degree of this function. Right. So recall the definitions. So you have the chain length, which is the maximum. You have to create a chain of functions leading up to that function, and you want to show a bound on the number of functions in your chain. You want to give a bound on the derivatives and the degree of the polynomial. Right. So let me work this example out. So one interesting aspect is that there's not necessarily a unique way to do this. You can come up with different Pfaffian chains, and they might have different degrees. So you want to do it in a somewhat smart way so that at least you can give an efficient bound of these quantities. So here you can come up with you can just put the entire function as in your chain. You can put your function f1 as just this entire function, right? Take its derivative, and you realize that can be expressed using